We're looking at the modeling environment right now. This is where the magic starts. It's a node-based interface, so instead of writing thousands of lines of code, you just drag and drop components. For this demo, we've loaded the gear unit example from the data library.
Right. You can see I've already added our design variable nodes for things like tooth number and module. But Sam, what if I need calculation logic that isn't in the standard library?
That's the low-code part. You simply drag in a black box function node. You can type your logic directly in Python using the built-in editor. In this block, we're calculating center distance, transmission ratio, and output speed. Once you hit Build Model, PyLCSS compiles this entire graph into a high-performance executable.
And I noticed it's checking my connections automatically.
Exactly. It has real-time validation. You try to connect incompatible data types or units, like connecting a Newton output to a meter input, the system flags it before you even run the simulation.
Now, let's talk speed. This gear model is simple, but what if we had a massive FEA simulation that took an hour per run?
That's where the surrogate capabilities come in. Look at the custom block node settings. We can check the Use Surrogate box and click Train Model. This lets us generate a dataset from our slow model and train an AI approximation using scikit-learn or even a PyTorch neural network right here in the application.
I can see the RMSE and R-square metrics updating in the Training tab to show how accurate the AI is.
Precisely. Once trained, we just switch the node to Enable. Now, that slow simulation is replaced by a surrogate that runs in milliseconds. It makes large-scale optimization feasible for even the most complex engineering systems.
Okay, the model is built. Now let's see what it can actually do. I'm switching over to the Solution Space tab.
This is my favorite part. Most tools just give you one best point, but PyLCSS looks for the entire valid design region. We've set our requirements on the quantity of interest nodes, like keeping center distance under 1 meter, and now we're running a Monte Carlo analysis with 3,000 samples.
Look at that visualization. The engine isn't just checking pass-fail, it's calculating the largest feasible hyperbox. We can see exactly which ranges of module and tooth number are safe to use.
And this is key for product families.
Right, because we can look for communalities.
Exactly. Instead of designing a unique gear for every single customer, we can identify the shared safe zones in the solution space. This lets us select one standard design that satisfies multiple different performance requirements simultaneously.
Now, if we want to get even more specific, we can jump into the Optimization tab. Let's say we want to maximize speed, but minimize center distance at the same time.
Those are conflicting goals. As it runs, we can monitor the convergence. But before we wrap up, Alex, I want to know which variable actually matters most.
Then we should check the Sensitivity Analysis tab.
I'll run a Sobol analysis here. This calculates the variance-based sensitivity indices for every input.
Interesting. It looks like tooth number has the highest total effect index on our weight, while theta is negligible. That means we can fix theta to a constant value and simplify the optimization problem significantly.
That's PyLCSS in a nutshell. Visual modeling, deep statistical insights, and AI acceleration all in one platform.